Welcome to this explainer. Today, we're decoding the universal accounting system for energy that dictates, well, absolutely everything around us. From the simple act of ice melting in your glass to the hyper-advanced green technologies that are going to power our future, it all comes down to the laws of chemical thermodynamics. I am so excited to guide you through this because honestly, once you grasp these principles, you'll literally see the world differently.
Okay, quick look at our roadmap. We are going to cover the universal accounting system, move into energy, heat, and work, tackle entropy and universal chaos, break down Gibbs free energy and equilibrium, and finally, talk about mastering your future. Let's jump right in.
Section 1. The Universal Accounting System, Nature's Ultimate Tug-of-War.
So, we have to start with a fundamental truth. Every single time a change happens in the universe, energy is actively being transferred and transformed. And thermodynamics, it's basically a massive cosmic tug-of-war. On one hand, you have the drive towards lower energy. Things in nature fundamentally prefer to just relax. Think of a heavy boulder rolling down a steep hill just to rest comfortably at the bottom. It wants to release heat and lower its energy state. But competing against that is the universe's inherent push towards higher disorder. The universe actually favors messiness, randomness, and dispersion over strict, rigid organization. This delicate balance between the pull to release heat and the push to spread things out, that is the driving force behind everything.
Moving to Section 2, Energy, Heat, and Work, the core laws in action.
Let's see how this invisible rulebook plays out right in front of your eyes. I'm going to speed run through a few everyday examples to prove that thermodynamics is constantly at work. Ready? When you sweat on a hot day, that's an endothermic process. The sweat absorbs heat from your body to evaporate, which physically cools you down. Same with baking a cake. It needs a continuous endothermic input of heat to make the batter rise. On the flip side, we have exothermic processes. When an iron gate slowly rusts, or when you ignite LPG on your stove, chemical energy is being released rapidly as heat. Heck, even when your smartphone battery gets mysteriously warm while charging, that's just thermodynamics reminding you that no energy transfer is 100% efficient.
Which brings us perfectly to the first law of thermodynamics. The crucial point here is that energy cannot be created or destroyed. That formula, delta U equals Q plus W, is just telling us that any change in the internal energy of a system is a strict, exact accounting of heat added, that's the Q, and work done, that's the W. It is a perfect ledger.
To really ground this math in reality, just imagine pumping up a bicycle tire. You're manually compressing the air, pushing down hard on the handle. You are doing mechanical work on that gas. Now think about the tangible heat radiating into your hands from the metal cylinder of that pump. Even without adding fire or a heater, the mechanical work you did increased the gas's internal energy. And that manifests as a physical temperature rise you can literally feel.
Building on that internal energy, we have enthalpy, represented by the letter H. Now, since most of our life happens out in the open where atmospheric pressure is constant, we use enthalpy to measure the total heat content of a system. The change in enthalpy, or delta H, tells us exactly how much heat is absorbed or released when the pressure around us isn't changing.
A brilliant illustration of enthalpy in action is just boiling water in an open pot in your kitchen. The atmospheric pressure in your room remains completely unchanged, right? So all that heat energy supplied by your stove goes directly into doing one very specific job, breaking the intermolecular bonds of the liquid water to turn it into steam. That heat absorbed at constant pressure, that's your change in enthalpy. Next up, we look at heat capacity. You can think of heat capacity as how stubbornly a substance resists a change in temperature. Different materials require vastly different amounts of energy to warm up by even a single degree.
And you've absolutely felt this mathematical difference if you've ever sprinted barefoot across a boiling hot beach on a summer day. The sand has a really low heat capacity, meaning it takes very little solar energy to make it painfully hot. But when you finally hit the ocean, the water is perfectly refreshing and cool. The crazy thing is, the ocean absorbed the exact same solar energy from the sun, but because water has a remarkably high heat capacity, its temperature barely budged. And beautifully, it's this exact difference in heating that drives the convection currents, giving us those amazing coastal breezes.
All right, Section 3, Entropy and Universal Chaos, the second law of thermodynamics. Let's transition from heat and energy to the universe's absolute favorite thing, total, irreversible chaos. The second law introduces entropy,
denoted by S, which is literally the mathematical measure of randomness or disorder. If you look at the total change in entropy of the universe, it is always greater than or equal to 0. The law mandates that the total disorder of the universe is always increasing. Things naturally go from orderly to messy, never the other way around, unless you force them to.
You experience this universal drive toward disorder all the time. Think about the delicious, or maybe not so delicious, aroma of lunch in a school cafeteria. When the food is cooked, the scent molecules are highly ordered and concentrated right in the kitchen, but spontaneously, they drift and scatter down the public hallways. They spread from a highly concentrated state to a scattered, disordered state. The entropy of the system increases simply because those gas molecules naturally want to disperse.
Section 4. Gibbs free energy and equilibrium, the ultimate deciders of reality.
Now we reach the absolute climax of our explainer. With enthalpy pushing for lower energy and entropy pushing for more chaos, how do we definitively predict if a reaction will actually happen on its own? Well, Gibbs free energy synthesizes our tug-of-war into one elegant master equation. Delta G equals delta H minus T delta S. This formula is the ultimate predictor of spontaneity. It perfectly balances the heat content against the temperature-dependent disorder. If delta G is negative, the reaction happens spontaneously. It is the definitive mathematical decider of reality.
A rusty park bench is a perfect physical manifestation of a negative change in Gibbs free energy. Think about that old bench in the park. Nobody's powering it with a battery, nobody's forcing it to change, yet it naturally tarnishes and corrodes over time. The metal is spontaneously achieving a more stable state by reacting with the environment, perfectly executing the balance dictated by that exact Gibbs equation.
But reactions don't always just go strictly in one direction forever. When the forward and reverse rates of these reactions finally balance out perfectly, we hit chemical equilibrium. The equilibrium constant, K, is deeply tied to the standard free energy and temperature, and the Van 't Hoff equation helps us understand exactly how temperature shifts this delicate balance.
Let's bring this to a party trick. Let's talk about opening a sealed soda bottle. Inside, the dissolved carbon dioxide and the pressurized gas are at a perfect dynamic equilibrium. But the moment you unscrew the cap, you cause a sudden pressure drop. You violently disrupt the equilibrium. So, to adapt and establish a brand new balance under atmospheric conditions, the dissolved gas rapidly escapes the liquid as fizz. It's not just bubbles, it's chemistry rushing to find its new equilibrium as dictated by the Van 't Hoff equation.
So, with all these master formulas, everyday examples, and physical sensations established, we have to pause and ask the ultimate question. Why does mastering this invisible rulebook actually matter for your personal future?
Section 5. Mastering your future, from competitive exams to global innovation.
The reality is, the rules of thermodynamics aren't just academic trivia. They are the gatekeepers to your immediate academic goals. For ambitious students, you know the names of these exams: IIT-JE, NEET, BITSOT, ISER, NEST. In these highly competitive arenas, simple rote memorization won't save you. An ironclad conceptual grip on Gibbs free energy and equilibrium is absolutely required. You need to deeply understand the physical reality behind the formulas to navigate tricky, multi-step numericals and secure those crucial marks. Thermodynamics forms the bedrock of physical chemistry and overlaps heavily with physics, making it vital for your success.
And beyond those exams, thermodynamics is literally the foundational language of global innovation. Whether you want to optimize sustainable factories in chemical engineering, design next-generation semiconductor wafers in materials science, or engineer the highly efficient EV batteries that will power our transport, thermodynamics is your primary tool. You will use these exact principles to tackle global challenges like climate change and drive the circular economy.
I'll leave you with this powerful thought. Understanding these principles right now in your studies is the first critical step toward becoming the innovator equipped to design the technologies of tomorrow. So, will you be the one to harness this relentless flow of energy to innovate our green future? Or will you let the universe's chaos dictate the terms? The formulas are in your hands now. Thank you so much for joining me on this explainer, and keep questioning how these invisible rules shape your world.